Study Unit 7, Lecture 2. So this lecture expands on Lecture 1, but expands the DC to AC conversion to three-phase DC to AC converters. Shown in the diagram is a three-phase DC to AC converter. Each phase is supplied by two thyristors and two diodes. The structure is analogous to the single-phase converter, where there were two legs with a load between the two legs. For the three-phase case, this is not quite the same because the load will either have a star network pattern over here or a delta network pattern. So in this configuration, power might flow from the DC supply through to terminal R, through the load to terminal Y, and then back towards the supply. An important characteristic of these types of converters is that each part of the load, whether it is a star network or a delta network, will only conduct through one part of the load at a time. In the case of the star network, through only one path through the network. What this means is that the legs of the DC to AC converter do not all conduct simultaneously, and in fact the controlling signal or the firing rate are all 120 degrees out of phase. So shown in this diagram is a simplified DC to AC converter. The diodes and thyristors have been replaced with ideal switches, and the load is being modeled as a star or Y network. What's also shown are the various waveforms which determine the behavior of the switching network, as well as waveforms which indicate what the output looks like. So in general there are two types of conduction schemes, where a conduction scheme is a control sequence or pattern in which these switches are switched. So there is a 180 degree conduction scheme and a 120 degree conduction scheme, and both will be discussed in this lecture. So during 180 degree conduction, what this means is that the switches that are in series, so in this case pairs T1 T4 or T5 and T2 or T3 and T6, are 180 degrees out of phase, which means that when T1 is closed, T4 will not be open. The same can be said for the other legs. 180 degree conduction does not specify which switch must be closed and which must be open. It only specifies that any series connected switch may not be open or closed at the same time. So before we break down how this thing actually works, just to describe the diagram, there are three sets of graphs over here. The first is a graph which shows the on and off periods of the switches. So there will be an on and off period for T1, T2, T3 and so on. The second set of graphs shows the line to line voltage, and this is the voltage behavior from one terminal of the star network to another. The final set of graphs show the line to neutral voltages, and these are the voltages across each respective resistor with regard to neutral. So there are several ways to describe the behavior of the switching cycle. I'm going to focus on the more sort of digitally inspired way of describing the switching behavior. During the entire cycle there are 6 different intervals. In other words, there are 6 periods where there will be 6 unique switch combinations, and these 6 combinations can be enumerated digitally with binary codes. So what this means simply is that each particular state has a unique binary identifier. The reason binary is used instead of just state 1 through to 6 is because by using the binary representation there can also be an indication of the on and off state of each leg. So for example, this first state here is 110, means that the first leg is on, so 1, the second leg is on, so another 1, and this leg is open, so 0. Using this enumeration as a basis, a really useful diagram can be constructed which shows the switching sequence and what type of switching can be accomplished using this network. So shown here in the figure are the 6 switched states. There are more states, but these are the 6 useful states which allow for AC generation from a DC source. The switching intervals can be arranged in a hexagonal star pattern as shown over here. Each arm represents a specific state and a specific order, and the way these things have been set up is that to move from or transition from one state to the next only requires one switch to change polarity. So for example, here is the 001 state. To move to the 01 to the 101 state, only one switch has to change the configuration. So here is the 001 state, and to change to the 101 state, only the first switch over here needs to change. And this will be true regardless of what direction is moved through the hexagon. So if there is clockwise or anti-clockwise movement, there will only ever be one switch which changes state. So using this configuration, there is never a state where all the switches are closed or all the switches are open. So to summarize, each of these switch vectors will only allow for a single switch to switch at a time, and this reduces the stresses on these switches. There will never be a case where they're all open or closed. And secondly is the dwell time for each vector. So the dwell time is the same regardless of which state the state vector is in. So how this translates graphically to these graphs over here, what it simply means is that there will be one condition where the switches will have a certain state and it will remain in that condition for pi over 3 of the full switching cycle. So the Fourier expression for the voltage of each line with respect to neutral is given by the following equation: 2 over pi multiplied by Vs multiplied by the sum of sine n omega t over n. N will be equal to 6r plus minus 1, and r can vary from 1 to infinity. This expression is generalized and can be used to describe the line to neutral voltage of any of the terminals of the three-phase load. So for terminal R, the voltage is 2 over pi multiplied by Vs multiplied by the sum of sine omega t plus 1 over 5 sine of 5 omega t, and so on. And this generalized equation can be applied to any of the terminals of the three-phase load. The only difference is that omega t needs to be substituted for the relative phase in that particular branch of the load. So for example, to determine what the voltage is for terminal Y with respect to neutral, then omega is simply substituted with omega t plus 2/3 pi. A similar approach can be used to determine what the line-to-line voltages are, and these are detailed in the reference material. The most important characteristic to take away from this is that this switching scheme emulates three-phase AC behavior through a load. An alternate switching scheme is called 120-degree conduction, and the idea between 120-degree conduction is to have a dead zone between conduction periods, and the idea behind this is to prevent any sort of parasitics or non-ideal switch behavior from resulting in two switches conducting at once. So a 60-degree dead zone is enforced to ensure that a switch has either opened or closed sufficiently before the next switching cycle starts. So if we're looking at, for example, the switching phase between T1 and T4 with 180-degree conduction, the first part of the cycle, T1 will be on, and then halfway through T4 will turn on and T1 will turn off. With 120-degree conduction, there will be a dead zone over here to ensure that there is almost absolutely no overlap between the conduction of T1 and T4. The disadvantage of this improved sort of safety margin is that the RMS output voltage using 120-degree conduction patterns is lower. So there are several techniques which can be applied to modulate the frequency and output voltage for these DC to AC converters, and I'll quickly touch on some of them throughout the lecture. Just to list the main ones which are referenced in the reference material, there is variable voltage DC link, single pulse width modulation, multi-pulse width modulation, multi-pulse width but with selected notching modulation, sinusoidal pulse width modulation, triple N injection, and finally selected harmonic elimination. So some of these techniques are fairly simple, others are far more involved. One of the simplest ones is variable voltage DC link, and what this simply means is that the input DC voltage is modulated or varied, and doing this will vary the output voltage of the DC to AC converter. Single pulse width modulation applies the quasi-square wave technique used for the single phase DC to AC converter to the three-phase converter. So what essentially is happening here is that there is a quasi-square wave used, or quasi-square wave base technique used for each leg of the converter bridge, and in this way the pulse width can be varied for each phase. In multi-pulse width modulation, The amplitude of the modulating reference sine wave can be altered, and by altering this, the point at which the sine wave intersects with the reference pulse train will vary the notch width of that pulse train. So here where there is a low amplitude, the notches are quite wide apart and the pulses are quite narrow. Here where the sine wave amplitude is quite high, the notches are very narrow and the pulses are quite wide. This multi-pulse width modulation scheme can be expanded to multi-pulse with selected notching modulation. With selected notching modulation, the on-off times of the notches can be varied, as well as the number of notches which are present. The final scheme that I'm going to discuss in this lecture is one which is used quite commonly, and that is sinusoidal pulse width modulation. In sinusoidal PWM, a reference sine is used in combination with a sawtooth signal to generate the timing, or rather the switching pulses, which are used to switch the switches in the DC to AC converter. There are several ways in which this can be done, and they are categorized into one of two categories. The first is natural sampling, and the second is regular sampling. First going to discuss natural sampling, and then move on to the regular sampling technique. So within natural sampling, there are another two categories. The first is synchronous, and the second is asynchronous. So for the case of a synchronous carrier, the sinusoid which is generated as the reference is synchronous to the sawtooth which is generated to ultimately generate the controlling pulses. What this means is that the frequency of the carrier wave is some integer multiple of the sawtooth. More correctly, the frequency of the sawtooth wave is an integer multiple of the fundamental sinusoid reference. So what this means is that there's always going to be an integer value of sawtooth pulses in a single half cycle of the reference. Another contributing factor is whether or not the integer multiple which relates these two frequencies is odd or even. If the integer multiple is even, then there will be even harmonics. If the integer multiple is odd, then there will be odd harmonics. These harmonics will then propagate through to the output voltage. If there is no integer multiple which relates the sawtooth to the fundamental, then the modulation is said to be asynchronous. So to consider all these things graphically, in this diagram over here, there is the reference sinusoid as well as the sawtooth wave which is also generated. The intersection of the sinusoid and the sawtooth will determine when switching happens, and this will generate the pulse train which will control the switches in the bridge. The pulse width or notch width can be controlled by varying the amplitude of the reference signal, because this will determine where the intersection is between the sawtooth and the reference sinusoid. So as can be seen here, much like many pulse width modulation schemes, there is a distinct difference between the pulse train generated by the high amplitude sinusoid and the pulse train generated by the lower amplitude sinusoid. One of the advantages of such a system, if implemented correctly, is that the commutation losses which would normally be present can be reduced, and the control circuitry can also be made quite simple. The problem comes in is that if the design is not that good, then there will be an asynchronous behavior which starts to creep in as the reference signal and the sawtooth start to drift away from each other. And what this means is that the system will start to behave like an asynchronous one. Essentially what the asynchronous behavior does is that the sinusoid will not resolve completely within one cycle. So what happens is that this pulse train starts to drift with frequency, and this will present as a very low frequency drift in voltage at the output. The more modern approach is to harness the advantages which come with any form of digital control, where this type of natural sampling will be formed with analog circuitry. A more regular sampling scheme can be implemented with a fully digital implementation. So in the digital case, the sampling period is determined by the controlling controller, or DSP or FPGA, whatever it may be, and the sinusoid which is generated from a memory bank of points which represent different amplitudes on the sinusoid. In fact, in a highly synchronous design, the sawtooth generation will also be tightly linked to the sample rate. So what happens, it is not much different from the natural sampling case, except now a discrete sinusoid will be generated. This is represented by the sort of blocky sinusoid over here. And each time, on each sampling interval, the value of the sinusoid in relation to the sawtooth will be measured digitally. This measured value will then be used to generate the PWM pattern. Once again, there are two small distinctions to be made. There is symmetrical modulation and asymmetrical modulation, and all this really means is that with the asymmetrical modulation, the sampling rate is twice that of the sawtooth frequency. And that's briefly the types of control techniques which can be used to vary the voltage and frequency in a DC to AC converter. There are more techniques which are discussed thoroughly in the text, and it is recommended that they be read. This concludes this lecture and a very brief discussion on VSIs. The next lecture will be on current source inverters.